Bismillahirrahmanirrahim. Assalamu alaikum. Uh, this is lecture number 7, chapter 7, digital transmission through AWGN channel. Previously, we discussed section 7.1, 7.2, and 7.3 from chapter 7. Today, we will discuss section 7.4 and 7.5. So in previous lecture, we discussed pulse amplitude modulation and its constellation diagram, which is one-dimensional. This constellation diagram is basically signal points for asymmetric PAM, pulse amplitude modulation. We also calculated average energy of the signals, equally probable signals. So if we look at if we look at the contents of the chapter 7, so we have covered section 7.1 and 7.2. So 7.1 is geometric representation of signal waveform, and 7.2 is pulse amplitude modulation. And we also discussed two-dimensional signal waveforms in section 7.3. So in section 7.3, we discuss baseband signal and bandpass signals. I hope you have gone through all my YouTube video links and listened to those the previous lecture, which was on carrier phase modulation, quadrature amplitude modulation, baseband signal, and bandpass signals. So today we will discuss section 7.4, multi-dimensional signal waveforms. So in this case, we have these topics: orthogonal signal waveform, bi-orthogonal signal waveforms, simplex signal waveforms, and band-recorded signal waveforms. Then we will move towards optimum receiver for digital modulated signals in AWGN channel, noise, AWGN noise. So let us come back to our slides. So section 7.3, I will quickly go through these slides which we have already discussed. So two-dimensional signal waveforms. So baseband signals definition, orthogonal signals, two signal waveforms S1 and S2 are said to be orthogonal over the interval 0 to t if their integration and after the taking their product is equal to 0. And the integration should be from 0 to t, which is the symbol duration. So two signal waveforms S1, S2 are represented like this. They can be, as you can see, these signals are orthogonal. Okay. So similarly, this set of signal is also orthogonal. And we can find the energy in the signal by taking the integration of square of the signal S1 square or S2 square. So this energy comes out to be A square T. You can put the value of S1 and integrate it from 0 to T, so you will get this energy. If we select the unit energy, the rectangular functions are the basis functions. Unit energy means that the energy is equal to 1. So in this case, we have these two basis function, phi1 and phi2. Since we are talking about two-dimensional signal waveform, so we need to have two basis functions. So then the signal waveforms can be represented in terms of these basis functions. as you can see, S1 is in term of S1151 plus S1252T. Similarly, S2T is S2151 plus S2252T. So this is 52T, and this is also 52T. This is 51, and this is 51. So it is a linear combination of signals. Then two-dimensional signal waveforms can also be represented by their vector notation. So S1 is a vector having S11 and S12. So the value of S11 is A times T under root divided by 2. Similarly, A under root T divided by 2. And for S2, the signals are A, T divided by 2 under root, comma, minus A, T by 2 under the root. The Euclidean distance between two signals is given by the difference. So take the difference of the two vectors and then square them and take the square root. So the Euclidean distance is under root 2 times E, where E is equal to energy, A square T. And similarly for another set of signal S1 bar and S2 bar, we have these vectors. So you see these two are orthogonal. S1 and S2 are also orthogonal because they have 90-degree phase. So we can build larger constellation for m equal to 4 for bi-orthogonal signal S1, S2, and minus S2 and minus S1. So this is for m is equal to 4 bi-orthogonal signals. So we can construct more complicated constellation diagram for like m is equal to 8. In this case, we have 8 signal points. So there are multiple options of representing the constellation. So in this case, we have 45-degree from one point to another. In this case, we have two different amplitudes and angles are 90 degrees. So you can see different possibilities are available. Two-dimensional bandpass signals carrier phase modulation, PSK. In this case, we multiply the baseband signal with the carrier, and the information is in the carrier. So we have different phases by taking 2 pi m over m. So we can take multiples of 2 pi over m. M goes from 0 to m minus 1, and the duration of the time is 0 to capital T. So two-dimensional signal waveforms continuing where G of T is the baseband pulse shape which determine the spectral characteristics of the transmitted signal. G of T is a rectangular pulse and the modulation is called phase shift keying. So this is the amplitude of that baseband pulse, and this is multiplied with the carrier. So this is a band pass signal. So waveform of BPSK, which is 2 PSK, and QPSK, which is 4 PSK signals can be represented. So this is the diagram for 2 PSK. As you can see, we have a phase of 180-degree shift. You see from this point. So in each time duration 0 to T, we have one signal, and then it is phase shifted by 180-degree from T to 2T. So it is 2 PSK. Or this is also called binary phase shift. Similarly, for QPSK or 4 PSK, 4 phase shift key. QPSK is 4 PSK. In this case, we have 4 phases. So the diagram looks like this. So from 1T, 0 to T, we have one set of signal. Then we have 180-degree phase shift, then another phase shift, then another phase shift. So we have four phases in this case. two-dimensional signal waveform constellation of two PSK, constellation of two PSK or any PSK can be uh, derived from this expression. So first of all, you have to find the band pass signal. Okay, then this sign expression can be expanded, uh, and then we can take cosine 2 pi m over m into cosine 2 pi fct cosine alpha plus beta. So it will be cosine alpha cosine beta minus sine alpha sine beta. So if you take this as beta and this is as alpha, so then this expression will be available. So we can represent this cosine 2 by m over m by AMC, and sine 2 by m over m by AMS. Okay. So in this is the general form of PSK signal. If we select the basis function as this one, then we can represent the signal in terms of uh, its vector. Uh, so we will have sine 2 pi m over m, which is AMC. So AMC into signal energy under the root. This will be the first point, and then comma. This is the second point. Okay. So in this case, by varying m, the value of m, we will get multiple constellation points. So constellation of PSK. So if this is the case of a binary PSK. This is the case of QPSK, where we have four constellation points. This is 0, and this is 1, and this is -2. So it is centered around 0. So this is the case of 8 PSK. So points are varying from 0, 0, 0 to 0, 1 to 3, 4, and 6, 7, 5, and 6. Okay. So this is actually using a gray coding scheme. Gray coding. So at one time, each one bit is actually changing from 001 to 011. So there is only change of one bit. So again, we have change of one bit here. Okay. So this is called gray coding. The Euclidean distance between any two signal points in the constellation can be calculated from this expression. So taking the difference, 2es minus 2es cosine 2 pi m minus n over m under the root. The minimum distance or the distance between two adjacent signal points is given by this expression. Then there is another possibility of differential phase shift keying. Differential phase shift keying means that if the phase difference is 0, we use a 0 bit. If phase difference is pi, then we take 1. Okay. So in each case, we have this is, suppose this is for and this signal is for bit 0. This is for 1. This is again for 1, 0, again 1. So if the bits are shown here 0, 1, 1, 0, 0. So this is BPSK. So DBPSK is different than this one. So in this case, if we look at this, we have more bits, one more bit. So initially it is 0, then again 0, 1, 0, 1, and 0. So the transition is from 0 to 1 in this case. If there is a 0, this is, you see that there is a phase difference of 180 degree from this point to this point. So the transition is from 0 to 1. Again, from here to here, we have no phase change. So that means 0, 1 to 0. Again, we have 0 to 180-degree phase shift. So the transition is from 0 to 1. Again, there is no phase change. So we have 1 to 0. So this is called differential phase shift gain signal. So if we take another form, which is called DQPSK, differential quadrature phase shift gain. So in this case, we are sending 2 bits at a time and 4 phases, 0, pi, pi by 2, and 3 pi by 2. So you can similarly track down how these bits are changing. So example, uh, please plot BPSK, DBPSK, QPSK, and DQPSK's waveform for a sequence of this one. So you can take two bits at a time, and then you can plot these the waveforms for these modulation schemes. The next case is a quadrature amplitude modulation, section 7.3.3. So in this case, we have positive signal here. Okay, so in the previous case, we had negative, as I can show you again. So in this case, we have negative here. And cosine 2 pi FCT here, FCT is missing actually. So this 2 pi FCT should be here. So in this case, quadrature amplitude modulation, this is the band pass signal. AMC and AMS are the sets of amplitude levels that are obtained by mapping k bit sequence into signal amplitude. So generation of quadrature amplitude modulation signal. So QAM signal can be viewed as a form of combined digital amplitude and digital phase modulation. Thus, the transmitted QAM signal waveform may be expressed as UMN is equal to AMG cosine FCT plus theta n. So we have to change, amplitude is also changing and phase is also changing. So how many bits can one QAM signal transmit? How many bits can one QAM signal? This is the question now. So this diagram is actually the function diagram of the modulator for QAM. So this, first of all, you have binary data, then serial to parallel conversion, then transmitting filter GFT on both sides, and then there is a balance modulator. Then this is oscillator, sine 2 pi FCT, 90-degree phase shift, and again balance modulator. So sine is shifted by 90 degree, it becomes sine 2 pi FCT, and then this signal is multiplied with this one. These two are multiplied and comes here, they are added together. Okay, so this diagram is actually for this expression. Okay, so GFT is actually your GFT is your pulse shaping function, and AMC, as I already mentioned, AMC and AMS, so are sets of amplitude levels. So bits are mapped to, k bit sequence are mapped to these signal amplitudes. Okay, so then these signal amplitudes comes over here, and after this function multiplied with this function, and then they are modulated by the carrier, and finally they are added together. So this is the diagram for a QAM. So we can use the geometric signal representation of the signals for QAM is given by this one. So symbol energy under the root AMC comma ES under the root AMS. So you can get these various amplitudes AMC and AMS by changing the values of M. So this is the diagram for M is equal to 64. So this is called 64 QAM. You see that the amplitudes are changing, and also phase will change from this expression. So you can get various values of AM and various values of theta n. So the coordinates will be the points will be changing their magnitude as well as their phase. Now we talk about section 4.1, which is orthogonal signal waveforms. So M is equal to 4 orthogonal signal waveforms are represented by this. So we have first set which is from 0 to A, then we have another signal from 0 to A, but again the amplitude changes to minus A, and then it alternates between 0 to A and minus A, and then again this thing is changing. So they are all orthogonal signals. 4 sets of signals which are orthogonal. So these are called baseband signals. Okay. So in this, now we have discussed in section 3, 7.3, two-dimensional signal waveform. We can also go to higher order, multi-dimensional signal waveforms. So the upper overlapping orthogonal signal waveforms can be constructed from header-merge sequences. This is a new term now, header-merge sequences, also called Walsh header-merge sequences. Generally, this two kinds of schemes is called waveform coding. Okay, so waveform coding is a very powerful technique of generating those signal waveforms. The waveform coding deals with transforming the waveform into better waveforms to make the detection process less subject to error. The encoding procedure provides the coded signal with better distance properties than those of their uncoded counterparts. So waveform coding procedure transform a waveform set into an improved waveform set. The improved waveform set can be used to provide improved PB compared to the original set. PB is your bit power. The most popular of such waveform codes are referred to as orthogonal and bi-orthogonal codes. The encoding procedure endeavors to make each of the two waveforms in the coded signal set as unlike as possible. So orthogonal codes, the signal set is said to be orthogonal if the cross correlation coefficient rho ij is equal to 0. Rho ij is the number of digital agreements, number of digital disagreements divided by total number of digital digits in the sequence. So it is the difference of number of digit agreements minus number of digit disagreement divided by total number of digits in the sequence. A one-bit dataset can be transformed using orthogonal code waveform code words of 2 digits each describing by the rows of matrix H1 as shown in the figure given below. So if we have data set 0 and 1, so we can generate an orthogonal code word set by a matrix 0, 0, 0, 1. Okay, so then the waveform can be plotted as, okay. So in this case, we have S1 signal and S2 signal, okay. So if you look at this, we have orthogonal wave code word set. So let us take a break here and let me take you to the book